Welcome to this fifth lecture in the programming language series. Today we're going to be looking at the LambdaCalculus. So the outline looks like this. First we'll be reviewing what computability is and Church's thesis. Then we'll have a closer look at the LambdaCalculus itself, at its syntax, and particularly the operational semantics, how we evaluate programs written in the LambdaCalculus. Then we'll have a look at the Church-Rosser property, which is actually tells us about this whole story of strict versus lazy evaluation, and we'll see how it applies in the LambdaCalculus and what this actually means for how we're able to evaluate programs. Finally, we'll go into a little exercise and see how with the LambdaCalculus we can actually model a lot of features that we know from programming languages. The material for today's lecture, a good deal of it comes from the classic article by Paul Hudak, which we've already seen before in the context of Haskell and functional programming languages. So, let's have a look at computability. What does it mean for something to be computable? So usually we think of computation as being a kind of a function, a mapping from inputs to outputs, which is being carried out by some kind of a machine. The machine could be something like a Turing machine, or it could be something which is a kind of a program which is executed by some kind of a formal machine. These machines work in a step-by-step fashion. So this comes back to our notion of formal semantics. When we assign a semantics to a programming language, we think of a machine which is somehow executing each of the operations of the program in a step-by-step fashion. And we'll see how that happens as well in the LambdaCalculus. Now, what kind of functions can we actually compute? So it's well known that there's certain kind of functions that we can think of that make sense mathematically, but we could never write a program or build a machine which could ever compute them. So an effectively computable function is one that can actually be computed in a finite amount of time using finite resources. But what actually is that? Alonzo Church, he came up with the following hypothesis. He said that effectively computable functions are just those that are definable in the LambdaCalculus, or, as it turns out equivalently, using a Turing machine. It turns out that pretty much any kind of notion of computability, whether it's LambdaCalculus or Turing machines or other kinds of computational abstractions, they all seem to be essentially equivalent. You can't prove this, so that's why it's a thesis rather than a theorem, because what we mean by effectively computable is an intuitive notion. It's not a strict mathematical one. You can only refute it by giving a counterexample. So you could come up with a machine that can solve a problem not computable by a Turing machine. And you could imagine such a machine mathematically, very highly parallel machines or whatever, but these are probably not machines that you could actually build in real life. So far, anything that anybody has been able to come up with has proven to be equivalent to Turing machines, or equivalently the LambdaCalculus. Now there are problems that are not computable. That's well known, and this should probably be reviewed for most of you. Assuming that Church's thesis is true, an uncomputable problem cannot be solved by any real computer. And the most well-known example of such a problem is the halting problem. So the halting problem, phrased in terms of Turing machines, given an arbitrary Turing machine and its input tape, will the machine eventually halt? This has also been formulated as, given an arbitrary program in your favorite programming language, can you write an analyzer that will analyze whether that program will terminate with a given input? Now, you can prove with a fairly nice constructive argument that the halting problem is provably uncomputable. You can construct a program that would lead to a contradiction if you could solve it. So that means that this cannot be solved in practice. And usually, proving that other problems are uncomputable reduces to showing that they're somehow equivalent to the halting problem or to some other problem that is equivalent to the halting problem. Okay, now, what do we mean by function? Essentially, in computer science, there are two fundamentally different ways of thinking of functions. The one is the extensional view, and the other is the intensional view. The extensional view is essentially the database view. And when we later look at the language Prolog, we'll see that Prolog supports both views. So the database view says a function is essentially a list of tuples that show how we map from a range A to a domain B. So a function in the extensional view is a subset of the cross product of A times B. So all of the possible values of A and B, such that if you have an A, then there exists some B, so there's always a mapping from an A to a B. And furthermore, there's a unique A. The A is kind of like a key. So if you have an A mapping to B's, then the resulting B value has to be unique. So that's essentially the database view. And in fact, when we talk about tuples in relational databases, we can say that a relation has a functional relationship when it fulfills exactly this property. The intensional view is the one that's closer to programming languages. So in this case, a function is a kind of an abstraction. So instead of actually listing the possible mappings from A to B, you abstract from the function and you write an expression which says how can you get from A to a value B. Essentially, this expression is kind of an algorithm. So with the help of the lambda calculus, we say that this function is an abstraction, lambda x, where x is a variable name, the argument to the function, lambda x dot e, where e is essentially the body of the function. It's an expression. It's an expression such that if you substitute a given a value, for the formal parameter x into the body e, then you can actually compute it. You can evaluate that body with that argument. And that'll give you some value b in the range big B. Okay, now let's have a closer look at the lambda calculus and its syntax and its semantics. So, the lambda calculus was invented by Alonzo Church as a mathematical formalism for expressing computations by functions. The syntax is absolutely trivial. We only have three possible syntactic forms. A lambda expression, a program, is either x, which is a variable. It's an abstraction, lambda x dot e, which says that I have a function with a parameter x and a body e, which can be evaluated. Or finally, a lambda expression could be an application, e1, e2, which says that e1 is a function, a lambda expression, that I can apply to the value of another lambda expression, e2. So e1 acts as the function, and e2 acts as its argument. So as an example, lambda x dot x is the identity function. It's a function that takes an argument x, and its body is also x. So when we apply that to something, we'll always get the same thing back. F of x is a function being applied to an argument. So here we see the syntactic forms. Lambda x dot x is an abstraction, and f applied to x is a function being applied to its argument. This is the same as writing f open parenthesis x close parenthesis, but we leave the parentheses off, just like we do in Haskell. In order to make lambda expressions easy to read and understand, we adopt some syntactic conventions. So the first of these is that we extend the lambda as far as possible to the right. So if you want to stop how far the lambda extends to, you have to put a parentheses around the whole expression. So lambda f dot xy, the lambda includes the f and the x and the y, so it includes everything. So you don't have to write it as lambda f dot parenthesis xy parenthesis. It's not necessary. And by default, application is left associative, so xyz means x is applied to y and the result of that is applied to z. This, by the way, is again the same as in Haskell. If you don't want left associativity, then you have to put the parentheses around the y and the z to force y to be applied to z before it's passed to x. And multiple lambdas can be suppressed. So instead of having to write lambda f dot lambda g dot x, you can simply write lambda f g dot x. Okay. Now, what is the lambda calculus? The core of the lambda calculus is its semantics. So how do you execute these programs? There are 3 rules for running lambda calculus programs. Actually, only 2 that are really important. One of these is a so-called conversion. That's kind of a refactoring. And the other 2 are the reductions. Those are the actual semantic operational steps. And of these 3, actually only the second one really does useful work. So let's have a look at what's going on here. Alpha conversion is a way of rewriting a function to an equivalent one. We know this from programming languages. It's a refactoring. If I have a function that takes an argument x, I can change the name of x and say, well, x is a stupid name. Let's call it n instead. So you can refactor and take every occurrence of x in the parameter list and in the body and replace it by something else. That's all that alpha conversion is. So here we see it, lambda x dot e can be rewritten, that's the arrow going in 2 directions, to lambda y dot e, and the thing in square brackets says we're going to rename every occurrence of x by y. So y replaces x in the expression e, everywhere where it occurs. As we'll see, we have to be careful about how the replacement is done, and that's why this thing in the square brackets with the slash is actually a very special operator in the lambda calculus. In fact, it was something that was studied carefully before people realized how critical this operation is. And this is related to the notion of free variables in programs, which we'll see shortly. So we can do this substitution as long as y is not free in e. We'll see a few slides later exactly what that means. But the basic idea is alpha conversion says that whenever we have a function with a parameter x, we can change that parameter to y, as long as we're a little bit careful about how the refactoring, the renaming is done. Now the second one, beta reduction, that's the really important semantic step in the lambda calculus. This is the workhorse that does the real work of computing a lambda expression. Here we see it. So on the left-hand side of the arrow, this is the expression we start with, and on the right-hand side of the arrow is the result. What does it do? Well, it simply says if I have a function applied to an argument, I can take that argument, bind it to my formal parameter, and stick it into the body, and then evaluate the body. So here's a function, lambda x dot e1. That's the function, and we're going to apply it to an argument e2. What does that mean? Well, it just means that we're going to evaluate the body e1 by replacing every occurrence of x by the value e2. So that's what we see on the right-hand side. So to evaluate the thing on the left-hand side, we're just going to execute the body e1, replacing every occurrence of x by e2. That's all there is to it. So that's one operational step. We have to be a little bit careful. So once again, we're using the special operator with the square brackets and the slash. That does the mapping, the replacement of the x by e2, being careful about name capture. Again, we'll see that shortly, why it's important and how it works. So it's not complicated, but you have to be, it's a little bit tricky, you have to be careful. And we'll see there's only one special case that we have to watch out for. The last one is a funny one, eta reduction. Eta reduction is a kind of an optimization. If we see an expression like lambda x dot ex, well, all that is a wrapper function. So if you have a function called fact, and I say, well, that's a bad name, I'd rather call it factorial. So I can define a function factorial. So factorial x is simply going to return me fact of x. The function doesn't really do anything, it's just wrapping, renaming, defining a function which calls another function. That's exactly what we have here. So lambda x dot ex is simply applying e to x. So it's the same as e. So if I apply this, the thing on the left-hand side, to an argument, it's the same as applying e to that argument. So all that eta reduction does is it removes the wrapper. So it's a refactoring as well, and a kind of an optimization. So the lambda calculus in the end can be viewed as the simplest possible pure functional programming language. Now let's dive a little bit closer and look at all of the details, look at each of these steps in more detail. So beta reduction is the most important of these semantic rules. And as I said, it is the computational workhorse, the engine of the lambda calculus. Let's look at an example here. So I is a so-called combinator. We'll see what we mean by combinators again in a few slides. And we defined it as lambda x dot x. So I is the identity function. And let's apply I to itself. So I of I should return I, right? So I'm applying identity, giving it as an argument I itself. It's the identity function, so to return what I give to it. Now let's see if this works in practice. So I applied to I is just lambda x dot x applied to lambda x dot x. If we look at that and look at our semantic rules, there's only one that we can apply of the reductions of beta and eta, and that's beta reduction. So how do we do that? Well, the first of these lambda x dot x has the body x, and we're going to take the second of these guys, lambda x dot x, and replace every instance of x in the body. So that's what we see in the arrow. So we've rewritten the expression blindly following the rule that we saw in the previous slide. So this says lambda x dot x replaces x in the body x. Well, that's a pretty straightforward substitution. We just replace that x by lambda x dot x. There's the substitution. But lambda x dot x is I. That's what we defined it to be. So we're getting back the result we expected. So in one execution step, we can reduce I applied to I back to I. So that's pretty much the simplest example of beta reduction that you can see in the lambda calculus. Now we can do exactly the same thing in Haskell. So let's have a quick look at that. Let's fire up the Haskell interpreter and we'll write in Haskell the equivalent of the identity function as a lambda. Now, as expected, if we apply this to a value like a number, or equivalently to a string, we get the same value back. The identity function is completely polymorphic and will work on various types. Interestingly, it will also work on functions. So applying the identity function to itself will yield the identity function. Unfortunately, Haskell doesn't know how to display the identity function, so it will complain if we try and show the result. But it works perfectly since we can apply the identity function to itself and then apply that to a particular value. In case you're curious about the application order, we can always force the application order to apply the function to itself before applying it to some particular value. Now, lambdas are just anonymous functions. We can write those directly in Haskell, or we can give names to them. So we just defined I in Haskell as being equal to the lambda, lambda x arrow x. But we can work directly with anonymous functions all the time. And that's what we do in the lambda calculus. Consider the following Haskell function. Compose, which takes arguments f, g, and x, and what it does is it applies f to g of x. Notice here we must put in at least the parentheses around g and x, because otherwise it would be parsed as f applied to g and the result of that applied to x, which is wrong. Now what's the value of compose? It's lambda f gx with the result f applied to g of x. So this is the same writing everything out in detail as lambda f dot lambda g dot lambda x dot f applied to g of x. So that's the same thing. Back to Haskell, let's look at the compose function defined as a lambda. So we can simply say let compose equals lambda f g x, which returns f applied to g of x. Or if you prefer to see it expanded out, we can say let compose equals lambda f, which gives us lambda g, which gives us lambda x, which gives us f applied to g of x. And now we can apply compose to a couple of functions binding f and g. For example, the function that increments x and the function that squares x. And apply that to your favorite number. Now, I mentioned earlier there's an important story of renaming that we have to be very careful. So when we're doing substitutions, we have to be careful about which names are free and bound to avoid so-called name clashes. Now, what's a free variable? A free variable is one that is not bound. A bound variable is simply one that is bound by lambda. This is analogous to, in programming languages, variables that are declared. So if I have a variable that appears in the arguments to a function or is declared somewhere to be an instance variable of a class or to be a local variable of a function, then those variable names are bound. They're bound by their declarations. In the lambda calculus, the only declaration is lambda. So when I say lambda x, that defines x and binds it in the expression e. Any variable that occurs in E that isn't bound is a free name. And as we'll see, free names can cause us some problems. A free name in a normal program is one that isn't declared anywhere. So if it's not declared, that usually ends up giving you an error either at compile time or runtime. We can define free variables recursively as follows. If I have the expression x, well, there's no lambda binding it, so it's free. So the free variables in the expression x is a set containing x. If I have an application of E1 to E2, well, the free variables of that expression is simply the union of the free variables in E1 and the free variables in E2. Finally, lambda is the binder, so it binds free variables, so we remove them from a free variable list. So if I have the expression lambda x dot e, the free variables in that are simply the free variables that occur in E minus x. That's it. Now, if an expression has no free variables, then it's closed. This is equivalent in a programming language to saying all the variables that we're using, they're all declared somewhere, which is usually a good sign. So particularly in Java, the Java compiler will be very unhappy if you mention variable names that aren't defined somewhere. So all Java programs should be closed. This is what's known as a combinator in the lambda calculus. So I, lambda x.x, the identity function, is a combinator because every free variable, x, is actually ultimately bound by its lambda. So there are no free variables in I. If I have the following expression, lambda y.x applied to y, the y is bound by the lambda, but the x isn't bound by anything. So x is free and y is bound. Now, here's a bunch of examples. I'm just going to skip very quickly through them now. When we have the question and answer session later, then we'll look at them all in detail. So these are all examples where you can reason applying the definition we saw earlier, and for each of these we'll have a look and see which are the free variables, which are the bound ones. So I also encourage you to have a look at these on your own before the question and answer session. Similarly here, hello world is a valid lambda calculus expression. Is it open? Is it closed? In the next section, we'll have a look at the Church-Rosser property. This is the one which will tell us about specifically how substitution works, and will allow us to reason about normal forms. First of all, let's see why macro expansion is wrong. Consider the expression lambda xy.xy applied to the expression y. Now this is a funny expression here because on the left-hand side, the lambda xy.xy, the y there is bound by the lambda x lambda y, but the one that's being passed in as an argument is free, at least within this scope. So by plain old beta reduction, what we would do is we would pass this argument y into the body of the expression on the left. Remember, we're dropping an extra lambda, so it's really lambda x dot lambda y dot xy. So by applying beta reduction, we're binding the y to the x. So the y is going to replace x in the body, and the body is what's left, namely lambda y dot xy. Now, something is interesting here. This y that's going to be pushed in and replace the x is going to cause us problems because we'll get a naming conflict. Because the y that appears in the body there, it's bound by the lambda, it's got its own definition, but the y that we're passing in the argument is a different y. If we pass it in as macro expansion, it's suddenly going to be captured. So this is name capture. It'll be captured by the lambda. And we end up with lambda y dot yy. This is completely wrong. So this is name capture, and we want to avoid it. So the y is already bound there. We cannot directly substitute y for x. So that's why we have to be very careful about the substitution function. The substitution operator has to be defined as follows. There are 6 different cases that we have to think of, and only one of them is tricky. So what we're defining is the thing in the square brackets with the slash. So we want to substitute e for x in some lambda expression. There are 6 different cases. The lambda expression could be an x, where the x is the same as the x that we see in the substitution, or it could be a y, which is different. It could be an application, or it could be a lambda, and there are 3 separate cases to consider with the lambda. Okay, so let's have a look at the first case. we want to substitute e for x in the expression x. Well, it's the same x, so we simply replace x by e, and we're done. That's the easy case. Another easy case. We want to replace every occurrence of x by e in the expression y, where y is not x. Well, then there's nothing to do. So the answer is simply y. So these two cases are super easy. The third one is the recursive case. It's also pretty easy. If we want to substitute e for x in the expression e1 applied to e2, well, we simply do the substitution on e1 and on e2, and we yield the resulting application of the two substituted expressions. Okay, now we have the three lambda cases, and we have to be careful. So the first one is where the variable x appears in the substitution. E is replacing x in the lambda expression lambda x dot e1. Well, this is actually a pretty easy case, because in e1 every x that might appear there is already captured by the lambda. So there's nothing to do. We can simply throw the substitution away. There aren't any free x's there. We can see that immediately because lambda x captures anything that might be any free x in e1. So there are none left to be substituted. Bang, easy case. Case number 5, so the second of the lambdas. Here we have ex. E substitutes x in the expression lambda y dot e1, where y is different from x. And in the e that we're replacing, there are no free y's. This is also an easy case, because the problem, as we saw in the previous slide, is where the e has a free y in it that might be captured by the lambda y. There aren't any, so there's nothing to worry about. We simply apply the substitution blindly on e1, on the body. That's the second easy case. The third case, so the last of the 6 cases, is the only tricky one. And this is exactly what we saw in the previous slide. We want to substitute e for x in lambda y dot e1, but e contains some of these y's. So what do? Well, we do a simple trick. We essentially do an alpha conversion. The problem is that the y will capture the y that's coming in e, but we know that function arguments can be renamed. So we perform a refactoring here. And the refactoring simply says, well, the y is causing a problem in the lambda y, so we're going to rename it something else. We'll pick another name, z, some name that's new, that we're not using anywhere. In particular, it shouldn't be in the free variables of e or the free variables of e1. So it has to be a new name that we don't see here. And we rename all the y's to z's, so that you can see that. And then after that, we apply the substitution e for x, which is essentially the same as the previous case 5. So the trick here is we rename y to z, and then we fall back to case number 5, where there wasn't any naming capture conflict at all. Here's an example. We have this big lambda expression, lambda x, with the body lambda y dot x applied to lambda x dot x, and that's applied to x, and that whole thing is applied to y. The little arrows there are showing you what binds what. So the big fat x's are being all bound by the lambda x. The thin x is bound by the embedded lambda x. So notice these, there are multiple instances of x, but they're bound by different definitions. Now we want to do a beta reduction, so the y is going to be bound to the x in this big expression. That's the first little arrow that we see there. So y replaces x in this expression, and now we see that this may lead to a conflict. So that's the case that we saw above, because this y, which is a free y, it's going to conflict with the lambda y.x. So we simply rename it. We do a refactoring, we change the y to a z, and suddenly there's no issue. And now we can plug in the y there, and there's no naming conflict. And we're done. So that's a little bit tricky. That's probably the nastiest part of the whole lambda calculus, but there's only one special case to watch out for. This whole notion of free variables and name capture is something that you can also see in programming languages. And when you write interpreters and compilers for programming languages, you have to keep careful bookkeeping of which names are defined where. That's essentially what we're doing here, is this bookkeeping, keeping track of which name is defined where, and make sure that we don't get confused about which variable we're talking about. Now let's go back to alpha conversion. Alpha conversion was this special rule that allows us to rename arguments to functions. So it's a refactoring. So if you have a bound name x in the lambda expression lambda x dot e, we can replace it by any other name y, as long as there are no naming conflicts, as long as we can't possibly get a name capture. And that is done with the help of the definition of free variables. So there should be no free occurrences of y and e. Here we see that. Lambda xy.xy applied to y. We first can do an alpha conversion, rename the second lambda, the lambda y, to lambda z. So the y's become z's. Then we do a beta reduction, and the y replaces the x in the body, and that gives us a lambda z.yz. Finally, we can do an eta reduction because that's just a wrapper, and we end up with the y. Let's have a closer look at eta reduction. This is the refactoring that lets you remove a wrapper. So suppose that f is a closed expression, a closed lambda expression, so there are no free variables in f, it's a combinator. Then, if I have the expression lambda x.fx, lambda x.fx with a beta reduction gives us fy. So in other words, this whole expression lambda x.fx is just behaving like f. In order to avoid the clutter, in order to get rid of such expressions, we have a special rule, the eta reduction rule, that recognizes that. So if we see any expression that looks like that, lambda x.fx, eta reduction will allow us to get rid of it, so that we don't get a beta reduction later. So it's just a wrapper around f, so eta reduction says, well, throw away the wrapper. Whenever x does not occur free in f, so f is closed, or f doesn't need to be closed, but we just need to make sure that x doesn't occur in it, then we can rewrite this expression as simply f. Here's a more extended example. So we start with this great big expression here, which is left associative. So the first lambda is applied to the second one before we apply the result to the third. So the first thing we do is an alpha conversion here. It's not required, but we can do it. So we rename the y to a z. Then we do a beta reduction. So we plug in the second lambda into the first one. That gives us lambda z with the second lambda applied to z as well, and that big lambda applied to the last one. We do another beta reduction, plugging the final lambda into the first one. Do another beta reduction, and that gives us this result. Another beta reduction gives us this, and finally we do an eta reduction to give us the resulting y. Alpha conversions are never really necessary to reduce an expression. we could have left out the first alpha conversion, and the beta reduction would have automatically forced us to rename the y to a z in the beta reduction rule itself, in the substitution rule itself. Now, the notion of a normal form is important. A lambda expression is in normal form if you can no longer reduce it by beta or eta reduction rules. You can always do an alpha conversion, so we ignore that. So as long as you can't reduce it anymore, then you've hit a normal form. So basically a normal form says you reach the end of your computation. Not all lambda expressions have normal forms, however. Consider this funny guy, omega. Omega is lambda x dot x applied to x, applied to itself. Let's try and do a beta reduction. So a beta reduction would take the second of these guys and plug it into the first. So into the first, which says take that guy, the lambda x dot xx, and replace every occurrence of x in xx. We do that, and bang, we get this expression which looks spookily like what we had a second ago, which is omega. So beta reduction step applied to omega will always give you omega back again. This is the equivalent of a Turing machine that never terminates. So this is a non-terminating expression in the lambda calculus. Once again, we have a few exercises. I'm just going to skip over them briefly now, and during the question and answer session, we'll have a closer look at each of them. The next important topic is that of evaluation order. Recall from our discussion with functional programming languages that most languages are strict. So a strict language says that the expressions passed into a function call are evaluated before you start evaluating the function. So in Java, if I apply method f to the argument 3 plus 4, well then 3 plus 4 is going to be evaluated first, strictly, giving us a 7, and then the 7 is going to be passed into the method f. In Haskell, if I say f is applied to 3 plus 4, that doesn't necessarily happen. So the function f may start executing and the expression 3 plus 4 will be passed in, and only when that value is actually needed will it be executed. That is, Haskell is lazy. In the lambda calculus, we didn't see anything so far that told us what the evaluation order should be. In fact, the lambda calculus does not insist on it. You can have a choice. You can evaluate things either way. So here, if we have the expression square of n is n times n, or equivalently lambda n arrow n times n, and we apply that to the expression 2 plus 5, well, in applicative order or strict reduction, we will first evaluate the argument 2 plus 5, giving us 7, and then pass it in to the body. Whereas in Haskell, like lazy evaluation, we'll pass that in first, and then only when we actually need the 2 plus 5 will we actually compute it, because to make now a beta reduction, we need in order to compute the multiplication, we need to know what the actual values are. Now here's the interesting property in the lambda calculus, and this tells us a lot about programming languages and why it's okay in languages like Haskell to be lazy. The Church-Rosser property says if an expression can be evaluated, it can be evaluated by consistently using lazy, that is normal order evaluation. If it can be evaluated in different orders, mixing strict and lazy, normal order and applicative, then, and they all give us a normal form, then all of the values are the same. And this is super cool. So it says that if in your programming language you could be either strict or lazy and mix them, and you get a result, no matter which way you do it, the result will be the same. Note that it does not say that you can always be strict, because being strict might lead to non-termination. So let's have a look at how we can use this in modeling basic programming constructs. First of all, non-termination is a problem. So in the lambda calculus, if we have the expression omega and we pass it into a function, if we're strict, that's going to give us a problem, because we're going to try and evaluate omega as the argument, and that's not possible. So if we try to be applicative, that is strict, we keep trying to evaluate the argument and not getting anywhere. So our program will not terminate. If we're lazy, we pass omega into lambda x dot y. Lambda x dot y doesn't even use an argument, it throws it away and gives us y back. This is equivalent to the Haskell expression, lambda xy giving a x, and giving it two arguments, 1 and 5 divided by 0. So lambda xy giving x will return its first argument, which is 1, and it'll throw away the second one. Because it's being lazy, it's doing normal order reduction, always doing the beta reduction on the left rather than on the right, and it will give us a result. The Church-Rosser property says if there is an answer, we can get to it by always being lazy. If you can get results by mixing lazy and strict evaluation, then they'll be the same value. In this particular case, being strict does not give us a result, so this is consistent with Church-Rosser. We do get a result by being lazy. In this case, we cannot mix lazy and strict, so there is no result, but that's consistent with what Church-Rosser tells us. Now, lambda abstraction only binds a single variable. Functions with multiple parameters could be modeled as curried higher order functions. In Haskell, we have tuples. We don't have tuples in lambda calculus, but as we'll see in a moment, we can model them. To improve readability, we left off multiple lambdas, just like we did in Haskell. So lambda xy dot x is the same as lambda x dot lambda y dot x, and so on. So this leads to fewer lambdas, fewer dots, and fewer parentheses. Back to Haskell again. We can let f equals lambda x y arrow x, so the function that returns the first of its two parameters, and apply that to the number 1. Or equivalently, if you want to see the lambdas expanded, we can see more clearly that this function is a curried function. So we can see here that lambda x, lambda y returning x is a function returning a function. So if we apply that to 1, we'll get the function which takes an argument y and returns 1. Let's see how we can model higher level abstractions that we know from programming languages in the lambda calculus. So far we haven't seen how to do anything really useful in the lambda calculus, anything that we would recognize as coming from programming languages. We can't do addition and multiplication and things like that, though next week we will see how we can even model numbers and arithmetic operations. Consider the following definitions. We're going to let the value true be the lambda expression lambda xy dot x. and false be lambda xy dot y. I think what they're doing. So we're modeling Booleans. Boolean as a function that takes two arguments, and true returns the first one and false returns the second one. Now we can model negation. Negation is a function that takes a Boolean as an argument and returns another Boolean. We'll see how it works in a moment. And an if then else takes a Boolean and an x and a y, where b is a Boolean either true or false, or an expression that reduces to a Boolean true or false, and x and y are arbitrary lambda expressions. So it's really a function in three arguments, a Boolean and an x and a y, and what we do, we simply pass x and y to the Boolean. Okay, looks a little weird, but let's see how it works. Not applied to true. Well, this is lambda b dot b false true, and it's applied to true, which is lambda xy dot x. We do a beta reduction, so the b gets bound to the value of true. There's the value of true, and it's being passed the arguments false and true. Well, true returns its first argument, so false. So not true is returning false. And it's trivial to see if you plug in not false, well, false will pick its second argument, so it'll return true. So not true is false, and not false is true. So far, Booleans and not are working the way we expect them. Let's have a look at our if then else. If true, then x else y. Well, and if then else simply passes x and y to its Boolean, and the Booleans either return the first or the second argument. Well, if true is going to return x, and if false is going to return y. So that's exactly what we expect. So we can model very nicely now some simple programming concepts. Now let's start modeling some data structures, starting with tuples. So we saw the lambda calculus doesn't have tuples, but we can model them using functions. Now get your head wrapped around this. Pair is going to be lambda xyz dot zxy. What's going on there? What pair is doing, it's going to take two arguments x and y, and it'll return to us a function, and that function will take as an argument another function and give x and y to it. So pair is really wrapping up the x and the y, holding them for later when a function needs them. And all it will do is it will pass x and y back to them. It seems kind of loopy, but as we'll see, it actually does precisely what we want to do. So here are two functions that could be clients of pair. First and second. The function first should return the first element in a tuple, and second should return the second element in the tuple. So first we'll take as an argument p, which is a pair, and it will pass into p the value true. And second, we'll take a p and pass false in. Well, as you recall, true and false were defined so that they take two arguments, and true will return the first one, and false will return the second one. Now let's add some extra syntax. So the syntax open parenthesis something comma something is going to represent pair of those two values. So paren 1 comma 2 is defined to be pair of 1, 2. So that's the syntax we're going to use. That's going to be lambda z of 1 and 2. Okay, so that's the pair, that's the tuple. So on the left-hand side we have the syntax, 1 comma 2. On the right-hand side, how we're going to encode it in the lambda calculus. Okay, so now let's apply the function first to our tuple. First applied to pair 1, 2 is going to be pair 1, 2 applied to true. This will then bind the value true to the z in lambda z.z12, and we get true applied to 1 and 2. And true then will return the first argument, which is 1. So it's working exactly as we expected. Let's have a look at how this will look in Haskell. Back to Haskell, we can see that we can program all of these abstractions directly in Haskell in a straightforward way. So we can let the truth value be lambda x, y, returning x. The false value be lambda x, y, returning y. We can let the pair function be the function that takes lambda x and y and passes them to a z. Now we can define the first function as the function which will take a pair and pass it the truth value. And second will be the function that takes a pair and passes it the false value. This all looks very mysterious, but if we unfold all of these functions, we'll see that they work exactly as expected. So if we construct a pair of 1 and 2 and pass it to the function first, it should extract the first value of that tuple. Similarly, we can navigate a more complex structure. So if we build a pair consisting of the value 1 and the second value being itself a pair, doing essentially a list-like composition, then we can extract the first of the second element from that construct in the way that we'd expect. So extract the second element of the larger structure, which is itself a pair, and extract the first element of that and gives us the value 2. That's it for this week. Next week we'll continue this exploration, and we'll see that in order to model more interesting kinds of programming constructs in the lambda calculus, we'll need a little bit more ammunition. In particular, we're going to need so-called fixed points, and we'll need a special kind of combinator in the lambda calculus to allow us to find fixed points, and this is the famous Y combinator. That's for next week. Thanks for your attention.